actually to miniaturize the size of the payload. So that's why we want to move from bulky instruments to sensors. That's one reason. The second reason is no matter where we go, okay, we don't have utility companies sitting there waiting for us. Okay, we have to generate our own power, and we have to be very wise how we use that power. So the sensors, not only they're small in size, but they also consume very low power. So that's why over the last decade or so, we've been working on developing nano-based chemical sensors, biosensors, and radiation sensors.
Now, when you're looking at these biosensors, and we're looking primarily for crew health, crew safety, what would they be used for?
What are the applications? Yeah, we've developed them for crew health and diagnostic purposes. That's our most recent project that we worked with the Game Changing Technology Office on. And so for that project, we developed this sensor to look at a variety of different protein biomarkers for cardiac health. And so when you're in microgravity, there's a lot of strain that's placed on the heart. So to monitor the health of the heart for our astronaut crew is critical. So that is the most recent technology that we developed for them. We've also worked on this sensor looking at microbial contaminants in the water supply. So this is an environmental kind of application for NASA to make sure that the water that the astronauts are drinking is actually safe to drink.
Now, when you're looking at the astronaut's heart, is it a sensor that you place on their body, or is it something they ingest, or what? How's...
This is an external sensor that will take one drop of blood and be able to screen for a number of different proteins. And depending on the levels of proteins and which proteins are present, we can make an informed diagnosis of the health of the crew member's heart.
Do these sensors have a long shelf life, or is it something that lasts for a short period of time because of the complexity of the sensor?
It depends a little bit on how we fabricate them and how we package them. The sensor itself, without any kind of surface modifications done to it, has a very long shelf life. I have sensors in my lab that are probably 10 years old that I can still pick up and use today. What limits the shelf life of these types of sensors is we often introduce some sort of biological probe molecule on that surface. So depending on what that probe is, that's going to dictate the storage needs as well as the shelf life of the device. We've been placing a lot of emphasis on making probes that are very robust so that we can increase that shelf life for our missions, so that we're not looking to replace these sensors every 6 months, that we can actually keep them for years at a time and continually reuse them.
And one of the coolest things that you were showing us this past week was the fact that you have a cell phone technology adapted to these nanosensors. So you have an application that you developed on the phone that can actually be used in concert with the nanosensor.
So this was designed actually for the chemical sensor project. And this phone has a plug-in port on one side that contains the sensor chip, has a fan that will direct airflow from the environment over the sensor surface. And then just using the electronics that are part of the phone, we have a nice little instrument that will actually read what kind of chemical environment the sensor is exposed to.
Now, would you have multiple nanosensors within that adapter for the phone, or is it just one nanosensor?
So we have one chip, but these chips can be made with a number of different sensors. They can have hundreds of sensors. They could even have thousands of sensors on one chip, all working together to tell the user of the phone what the environment is.
Guys, that was some great information on nanosensors. I can definitely see how that is a game changer, because once it's commercially available, it will definitely change our lives.
I tell you what, we could have spent a whole show on nanosensors. That's how cool the technology is.
That's right, Chris, but we're only scratching the surface at looking at this technology. I had a chance to sit down with Jim Geyer, and he explained how NASA is using nanotechnology to develop better, stronger wires. Let's check it out. Jim, I understand that you're working with carbon nanotubes as a potential replacement for conventional wiring, but I didn't know wiring needed an upgrade. What exactly are you doing to improve wires?
Well, I don't think a lot of people understand that wiring really takes up a large amount of the mass in current spacecraft and aircraft. Like a 747 has nearly 2 tons of wiring in it, and the Space Shuttle had almost 300 miles of wire. This is a lot of weight, and so conventional wiring with copper, it turns out is very heavy. Copper is dense, and it's also not very strong. And so we're looking for a way to have better mechanical properties, actually, than conventional wires have.
So these carbon nanotubes, when you make a wire out of them, how do they perform in terms of strength?
They're much stronger, they're more thermally conductive, so you don't get hot spots and so on. They're very flexible. They're actually much more flexible than copper, and they don't fatigue. Fatigue is when you get a breakage from moving back and forth.
That's how I break wire intentionally sometimes.
Exactly. And in fact, they ran tests and they were not able to run enough cycles to actually break these carbon nanotube wires. They finally had to give up and go on to the next test.
Okay, so the carbon nanotubes are stronger and they're lighter. How do they perform in terms of conductivity?
Well, conductivity is the issue. It turns out that carbon nanotubes, while theoretically have a very, very high conductivity, to use them practically, you have to make these bundles because an actual carbon nanotube is less than microscopic. And so to use them, we have to actually bundle them together. And when you bundle them together, you lose a lot of that conductivity.
And that's principally where your work is then. You're going to solve this conductivity problem.
That's our goal.
Okay.
Right. What we're doing is we are chemically altering the carbon nanotubes. We're doing a process called intercalation, which means to insert. And we are inserting halogen atoms. These are bromine, chlorine, iodine, in between the bundles. And when we do that, it makes the bundles actually much more conductive. And so what we're trying to do is get to the place where our conductivity is high enough that we can run these as electrical conductors. They're not going to be as conductive as copper, but because the wiring in aircraft and spacecraft is not limited by the conductivity, but by the strength, we're going to be able to save a tremendous amount of weight. We're in the early stages of our research, but we've already developed carbon nanotube wires that have a specific conductivity. That's a conductivity per gram equal to copper.
Well, solution, problem solved. That's great. No, that's a good step, right?
It's a good step, but it's not the only step. Okay. Because right now we're working with very, very tiny amounts. I mean, milligrams of material, and we're going to have to work with kilograms of materials. And so we have both the process of our partners who actually make these fibers have to scale up so that they can make large quantities, and we have to scale up our chemical processes so that we can modify them.
Okay, so scaling up is actually the big challenge.
It is.
Okay, see, for a second I thought if I understood this properly, I'd understand how Peter Parker could shoot web. Okay, but apparently with the scale-up issue, not even he could handle it at that.
I'm afraid not.
All right, well, appreciate it. I wish you the best of luck, and I hope soon to see copper wire. Well, I don't want to see them go away, but at least in terms of these aircraft and spacecraft, saving that weight and giving us all the conductivity we need.
I hope so.
It's interesting to see how NASA, as they improve on a technology, just how complex the process becomes. And I never would have thought about it, but creating nanowire is actually a groundbreaking or game-changing technology.
Yeah, and that's a cool area of research that Jim's working on. But another area that NASA's looking at is carbon nanotubes in overwrapped pressure vessels. So what they want to do is they want to take a COPV, or a composite overwrapped pressure vessel, and spin it with carbon nanotubes.
And those carbon nanotube composites are, as you said, very difficult to work with. So NASA is actually looking at a couple different approaches.
And I had an opportunity to look real closely at least one of those approaches. Let's check it out. We're here with Aslan Biagi, who's the project manager for nanotechnology. So Aslan, tell us about what you're doing with nanotechnology.
Our goal is to actually use the nanotechnology and make lighter materials so that we can reduce weight on the vehicles and launch vehicles.
And I understand you have a big flight test that you're moving toward.
Yes, so our carbon nanotube reinforcement composites that we're developing in the nanotechnology project will later be placed on a composite overwrapped pressure vessel, which will be launched on a Sounder rocket.